Hello chemists, this is Ms. Placino and you're watching lesson 10.5 on colligative properties. In today's lesson we're going to talk about how specific properties of a solution are going to differ from the properties of the pure solvent. Goals for today's lesson is to understand how adding a solute affects the colligative properties of the solvent. That's what we're really focusing on today. And you're going to want your calculator because by the end of the lesson you should be able to calculate changes in freezing point and boiling points based on the concentration of the solution. This is the big one for today's lesson. So let's go ahead and get started. So there are certain properties that are going to change when you take a solvent and you add a solute to it. Ultimately, you form a solution. These properties that are going to change are called colligative properties. Colligative properties are properties that depend on the number of non-volatile solute particles present and the nature of the solvent. When we say non-volatile, what we mean is does not easily turn into a gas. So a lot of our solid particles, things like salt and sugar, for example, those are non-volatile. Those are not going to easily turn into the gas phase and escape this solution. So with colligative properties, it does not really matter what the actual identity of the solute is. It doesn't matter if you're talking about sodium chloride or you're talking about glucose or sucrose or calcium chloride. These are properties that are going to change in predictable ways simply by adding one of these non-volatile solutes. It doesn't particularly matter what the solute is. So we're going to focus on three different colligative properties today. We're going to look at a change in vapor pressure, boiling point, and freezing points. All right, so here we have two different pictures for vapor pressure. We've got pure water on the left side, and then we've got some aqueous solution on the right side. If you'll recall from previous lessons in Unit 7, vapor pressure is the pressure of the vapor that's going to exist like above a liquid. And as long as you close off the container and you give it some time to equilibrate, you should end up with a constant number of vapor molecules present in, well, in this case, the Erlenmeyer flask. What do you notice is different about the vapor pressure of the pure water and the aqueous solution? Hopefully just at first glance you can kind of see that you've got a lot more water molecules in the vapor phase in our pure solvent than you do in the solution. So the effect of adding a solute is to cause the vapor pressure to decrease. So solutions will always have a lower vapor pressure than the pure solvent. If you think about why that might occur, there's a couple different explanations you can use. If you think about the pure solvent, every single molecule that's kind of at the top layer is going to be the solvent. It's going to be easy for that to evaporate because it's usually the particles up at the top that are the ones that are going to leave the liquid phase and become a vapor. If you look at the aqueous solution, not every single molecule that's in contact with like the air above it is water. So in this case, there's just like a lower likelihood of the water molecules being able to escape. Another way to look at it is through intermolecular forces. In addition to the hydrogen bonding that's going to exist between the water molecules, we're also going to see attractive forces between the solute and the solvent, making it more difficult for the liquid particles to evaporate and become a gas. This is going to have an impact on our phase diagrams. So you might remember a graph that looks something like this from, I think it's lesson 7.3 when we're talking about phase changes. So just to quickly review the phase diagram, we've got solids, liquid, and gas. And as we kind of move across this like black line for our pure solvent, we're going to undergo those phase changes. By adding a non-volatile solute to the solvent, ultimately forming a solution, kind of what you end up doing is moving these two lines. You can see the blue line kind of shows everything shifted down and to the left. So that's going to have an impact on our boiling point and our freezing point. If we look first at freezing point, you can see that the pure solvent has a freezing point that is greater than the freezing point of the solution. So we're going to see a freezing point depression. If you look at what happens to the boiling point, by adding a non-volatile solute, we end up increasing the boiling point. So the pure solvent has a lower boiling point than the solution. This is an increase or boiling point elevation. One way I try to kind of visualize this is imagine you're holding onto a thermometer. We know that the boiling point tends to be up towards the top of the thermometer at 100 degrees Celsius, and your freezing point is going to be down towards the bottom at 0 degrees Celsius if we're looking at just water as our pure solvent. If you imagine putting your hands, one on the top of the thermometer, one at the bottom of the thermometer, and just kind of stretching the thermometer, you'll see that the hand that's up by the 100 degrees Celsius goes up, kind of representing a boiling point elevation, and the hand that's down holding the freezing point is going to get lower as that thermometer is stretched to try to represent a depression of the freezing point. So that might just be a helpful way for you to remember that adding a solute to the solvent causes the boiling point to increase and the freezing point to decrease. I want to just kind of talk a little bit more about why we see these changes in boiling point and in freezing point. So if we take a look at boiling point, we've got our non-volatile solute added. In this case, it looks to be something like sodium chloride. And we're using water as our solvent. We know that water molecules are going to be attracted to one another through hydrogen bonding, a pretty strong intermolecular force. Now, in addition to the hydrogen bonds, what do we see going on here? What's being represented like in those two pictures? Hopefully you're looking at that and you're saying, oh, those ions are also attracted to the water molecules. This is what we'd call like an ion dipole intermolecular force or attractive force. So now, in addition to there just being hydrogen bonds present everywhere, we also have these strong attractive forces between the ion and the water molecule. So we have more intermolecular forces, so more energy will be required to get this substance to boil. This is why we always see the solution having a higher boiling point than the pure solvent. It doesn't matter if we are looking at a ionic compound getting dissolved, like we see here, or if we're looking at something that is covalent, a molecular solid like sucrose, for example. You're going to have an increase in the number of intermolecular forces, so you're going to need more energy to boil the solution, therefore a higher boiling point. Let's take a look at freezing point. We know that a solution is going to have a lower freezing point than the pure solvent. So let's take just a moment and talk about why that occurs. Anytime a liquid solidifies, we need to take our liquid particles that have usually a little bit higher energy, and we need to get them close enough so that they can form strong intermolecular forces, eventually leading to the formation of a highly organized solid. As soon as we throw something like salt particles in the solution, we've increased the entropy of the system. Now we've got to get to temperatures that are cold enough where the solvent particles are able to come together to form the solid, but the solute particles are left out. If you were to go to someplace with an iceberg, maybe like Antarctica, and you were able to chip off part of the iceberg and eat it, you'd actually find that it is not salty. You cannot freeze these salt particles, or ions more specifically, into the solid. They have to be kind of frozen out of the solid. This requires a lower freezing point temperature to do so. So we see this depression of freezing point regardless of the nature, or the identity, I should say, of the solute. All right, so we know that boiling point will increase and freezing point will decrease as soon as we add a solute to the solvent to form a solution. I want to talk about how much these two temperatures are going to change. And in order to do that, I'm going to use a couple of formulas. I've got this delta T sub B equals K sub B Mi. And a very similar looking formula, just kind of change those B's to F's. What we have here is the boiling point elevation and the freezing point depression formula. We know that the delta, that triangle, means change. T sub B is the boiling point. T sub F is the freezing point. So the change in the boiling point or the freezing point is going to be equal to some constant. It's going to depend on whether you're looking at boiling or freezing and what solvent you're looking at, times the molality of that solution. This is the time that we're really going to use molality instead of something like molarity, times something called I, which is the Van Hoff factor. And we'll talk more about that in just a moment. I'll provide you with these if you need them on something like a quiz or a test, but it's worth jotting down for your practice problems. The boiling point constant for water is 0.513 degrees Celsius per molal. So every time you have a molal of particles in your solution, or I guess I should say you have a solution with a molality of like 1 molal, you're going to see about half a degree Celsius increase in the boiling point. Your freezing point constant for water is negative 1.86 degrees Celsius per molal. So a 1 molal solution would have a freezing point of negative 1.86 degrees Celsius. This I, let's talk a little bit more about that. I is effectively the number of particles produced by the solute. So I want to think about these three substances, glucose, sodium chloride, and calcium chloride. Based on what you know about the nature of the bonds that exist between the atoms of these substances, I want you to predict how many particles would be produced by the solute in each case. All right, for C6H12O6, or glucose, that is a molecular solid with covalent bonds. When I take glucose and I put it in water, it will be solvated. In other words, it will be surrounded by water molecules, but the water molecules can't pull that molecule apart. So I is equal to 1. If I take a look at sodium chloride and calcium chloride, I know as ionic compounds, they're going to break apart into ions. We'll make a sodium plus and a chloride minus ion, so we'd have 2 particles, so I would be equal to 2. And with calcium chloride, we'd make a calcium ion and 2 chloride ions. So in this case, I would be equal to 3. In reality, there's a little bit more to it than that, but at this point in the game, I'm pretty okay with this explanation and this sort of calculation. So that's to say, if I was to have a 1 molal solution of each of these, even though concentration is the same, the number of particles that are floating around in solution are not. So I would see the biggest change in freezing point and boiling point from the calcium chloride solution. I would see the smallest change in boiling point and freezing point from the glucose solution. Let's try out this formula and do some calculations. I want to take a look at question number 1. 2 moles of glucose are mixed with 500 grams of water. What is the freezing point and boiling point of the solution? Okay. First order of business is to find the concentration in terms of molality of this solution. I know that molality is equal to moles of solute divided by kilograms of solution. So we have a pretty straightforward plug and chug here. I've got my amount of glucose in terms of moles already. And I can quickly convert in my head 500 grams to 0.5 kilograms. I can have 3 sig figs in this answer. I come up with 4.00 molal solution. Okay. Once we know the concentration, we can apply those 2 formulas we just talked about. We're asked to find the freezing point and the boiling point. So let's go ahead and do that now. I know that the change in the freezing point is going to be equal to the freezing point constant for water times the concentration of the solution times I. So we'll start plugging in what we know. I know that my freezing point constant is negative 1.86 degrees Celsius per molal. I know that the concentration of my solution is 4.00 molal. And I is the number of particles that the substance is going to break apart into. We just talked about glucose on the previous slide. Glucose, as a molecular solid, is going to not break apart, so I is going to be equal to 1. Hopefully from here it's just kind of a straightforward, plug it into your calculator and solve for the answer. When I do that, I come up with a change in freezing point temperature of negative 7.44 degrees Celsius. This is telling me how much my freezing point is going to change by. Conveniently enough, the freezing point of water is 0 degrees Celsius, so my change in freezing point is actually equal to the new freezing point. So the freezing point of this 4 mol solution of glucose should be negative 7.44 degrees Celsius. Let's go ahead and try to apply the boiling point formula. Now I should have reversed the colors. Blue looks cold. So I've got the change in the boiling point temperature is equal to the boiling point constant times the molality times I. There we go. So my boiling point constant for water is 0.513 degrees Celsius per molal times the molality of the solution, 4.00 molal, times 1. So my change in boiling point, if I grind through the calculation, and I will go to just 3 sig figs here, so you're going to have to do a little bit of number shaving, get about 2.05 degrees Celsius. A rookie mistake is to be so excited that you're done with the calculation that you say, oh, the new boiling point is 2.05 degrees Celsius. Whoa. Remember, you're calculating the change in boiling point. So this isn't the new boiling point temperature, this is how much the boiling point is going to change by. We know that the boiling point of water, because that is our solvent, is 100 degrees Celsius. So my new boiling point should be 102.05 degrees Celsius, not 2.05 degrees Celsius. I see that happen a lot. And when you think about it, of course, it doesn't make sense that the boiling point dropped by about 98 degrees Celsius. It makes a lot more sense that it increased by about 2 or so degrees Celsius. So don't fall into that trap. I can make this problem a little bit more complicated by giving you values that are going to have, or I should say compounds that are going to have I values that are different from 1. Be careful if you're looking at something that's ionic. But you can actually use this to figure out a lot of interesting things about a solution or about the solute itself. So definitely play around with those practice problems, get comfortable with this concept, and just keep practicing. All right, nice job with this, chemists. Thanks for tuning in, and I hope you found this helpful.